So now we're going to talk about this, the relationship between the sample size and the sampling distribution of the sample mean. And basically when you increase the sample size, so here sample size, before we were looking at sample size with n equals 30, and our standard error was 730.3, meaning this is the standard deviation of our sample mean. So we have a bigger standard deviation, which means that for each 1, 2, 3 standard deviations, we're moving farther out. It means this curve, this normally distributed curve, is going to be shorter and wider. So that's with sample size being 30. If we do sample size equals 100, our standard deviation is going to go down because we have more data points. So we're more accurately estimating the population parameter. Our sample is pulling more from the population and getting a better estimate of what's really going on in the population. And so here, our normal curve is the standard deviation isn't going to be as much, right? Here's our standard error, which is the standard deviation of the sample mean, and it's only 400. And so that's the relationship between the sample size and the sampling distribution. This is the sampling distribution. As the sample size goes up from 30 to 100, your standard error, or the standard deviation of the sample mean, goes from 730 to 400. So the standard error goes down, which means that each standard deviation is not as big, right? With a larger sample size, it's not as big. 400 is less than 730. 400 is not as big as 730. So you get a tighter curve with data more tightly clustered around the mean, right? Less deviations because you did a larger sample size. And so here's how that's explained. Suppose we select a simple random sample of 100 employees instead of 30. The expected mean, I just got to check to make sure I'm using the right terminology there, because I'm still learning this too. The expected mean, which was somewhere here, expected value, that's what I was looking for. I'm just going to copy this here and go, ooh, can I copy all that at the same time? Ooh, I got to do it like this, boom, like that. And it gave me all that. I don't need this up here, so I'm just going to bring that up. And I just want these, like, yeah, got it again. I just want this right there. Why does it keep giving me that? I guess this is in there. We'll take it all. And then we're going to come over here, and we're talking about this one here. And I'm just going to bring this down for a second. And then get rid of this stuff up above. Can I get rid of this stuff right up here? There we go. The expected value of x is equal to u regardless of the sample size. In our example, the expected value of our sample mean remains at 71,800. So maybe that's just, for this example. Whenever the sample size is increased, the standard error of the mean, which is the standard error, standard deviation of the sample mean, is decreased. And so we saw that here, right? The standard error went from 730 to 400. It was decreased as our sample size went from 30 to 100. So there's an inverse relationship there between them. Whenever the sample size is increased, standard error of the mean is decreased. With the increase from in the sample size to n equals 100, the standard error of the mean is decreased from 730 to 400. And so here's that math occurring. There's that picture we've been looking at. Recall that when n is equal to 30, the probability of 71,300 to 72,300, right, 500 on each side of 71,800, the probability of that is 50%, 50.34%. We follow the same steps to solve for p 71,300 to 72,300, and the probability of that. And when n equals 100, as we showed earlier, n equals 30, right? That's a confusing sentence, but it's just saying we're going to calculate this again with a different standard error, because the way you calculate that is you get your z-score, and your z-score is like this data point minus the mean. And in this case, it's 72,300 minus 71,800, which is the sample mean, the mean of the sample mean, right? And then we divide that by the standard error, and the standard error is the standard deviation of the sample mean. And so when we do that, the standard error, right, has a different value because the standard error is calculated here. Standard error is 400 now as opposed to 730, whatever it was. And so we get a different z-score, even though we're looking at the same values. So because the sampling distribution with n equals 100 has a smaller standard error, and it has a smaller standard error, n equals 100, because with n equals 100, n goes into which part. Hold on, let me just think about this here. How do we get the standard error going down? So the standard error going down, here is where the n goes in, and it gives us a smaller standard error. And then here, that standard error gets put here down in the denominator, a smaller standard error down there. And so that smaller value in the denominator, if this is a large value, and we have like, you know, the difference here would be 500 over, like, let's say 100, or 500 over 50, then 500 over 100 would be 5, or 500 over 50 would be 10, right? So our z-score, in that case, they got larger, but here the z-score is going to get smaller, and with a smaller z-score, it'll be tighter for our data. And I just got to think about why it's getting smaller. Hold on one second. All right, so let's actually work this out on our own. And I was just finding myself like too many things to track in my brain, and it's a little bit late. So let's have one situation where we have, we need to calculate the standard error for each of these. So I'm going to do this, and we'll do this one here, over here. And we're going to have one situation where our sample size, we're doing a sample size of 100 and sample size of 30. Okay, so here it's like n is equal to 30, and here we're going to do n equals 100, and then we'll just make this all a little bit smaller so we have more room to work with. So we'll make that smaller, and I think I'll make this like 14 actually, and then we'll make this one 14, and oops, I want it 14. And I'm wondering if there's like formatting and line and paragraph spacing and single and remove space before, and format, line and paragraph spacing, remove space after, and we'll do that up here too. So format, line and paragraph spacing, remove space before, and format, line and paragraph spacing, remove space after. All right, so now we want to calculate our standard error. And so our formula for our standard error is going to be, if we have 30 or more, then we could use this formula here for our standard error, and it's going to be the standard deviation over square root of n. And standard deviation for our population in this situation is 4,000. So here it is right there, 4,000. That's just given to us in this diagram. And so we need 4,000 over the square root of our sample size to get our standard error. And so our standard error is going to be equal to, it's going to be equal to 4,000, which is our standard deviation for the population, divided by the square root of 30. And that's all going to be like that. So that's what we need to calculate. And then we're going to calculate this also over here. So I'm just going to bring this over. And again, this is a standard deviation for the sample mean. And so to calculate that, we could do spreadsheets. And so a spreadsheet's going to be the best way for me to do that. And we're going to go into Module 7, and we'll do a new spreadsheet. And we'll create this. And we're going to have 4,000 here, and we're going to have 30, and then we're going to have 4,000 here. And we're going to have 100, and then the square root of that is going to be equal to square root. And so the square root of 30 is that, and we'll copy this over, and the square root of 100 is 10. And then we're going to have equals the 4,000 divided by that square root of the sample size. And so that's that one, 730. And then this one is 400. So this will be 730.3. And the other one is 400. So here we have, it's equal to 730.3, and this one is equal to 400, okay? And so with a larger sample size, our standard error went down in size. And then the next thing we want to calculate is what is our z-score. And z-scores, and for, 71,300, so 71,800 minus 5. So here's our situation, 71,800 minus 500, 71,300 plus 500, 72,300. So we need a z-score for that, and we also need a z-score for 72,300, right? We went $500 on each side of 71,800. So we're going to calculate those z-scores, and to calculate a z-score, our z-score is going to be equal to this data point, a data point minus the mean. So the data point we're looking at here is 71,000. It's going to be 71,300 minus the mean, which is 71,800. And that's going to be divided by our standard deviation, which in this situation is our standard error of 730.3. And so that's going to be the formula that we're going to do there. And then we're going to do the same formula here, but for this. And I'll put that there. And that's going to be 72,300. And then I could copy all this over here. And we'll just put all this here. And instead of being with 730, it'll be 400. And so if we have less here, it's going to make less amount here. It's going to make our z-score bigger, right? So our z-score gets bigger here. So let's just see, and then we'll go look it up. And so when we do this formula here, I could just drop this into Google actually, and it'll calculate that for me. It's that amount. So I'm going to just copy this. I wish there was like a little copy button there, but there's not. So I'm going to come over here and put that there. And that's a negative, right? It's negative. Let's just bring this over here. Yep, negative. And then our z-score here is going to be the positive of that. And put that down with this one, don't that one. Put that here. And then this one here is going to be that. And so with, yeah, cool, I got it. And then with smaller value in the denominator, we got a bigger z-score, right, which makes sense. And then we can look these up. So if we go to our z-tables, so here's our z-table, and we're looking for negative 6.8. And so we have negative 6.8, and 6.8 is 0.2483. And so that's 0.2483, right? And is that negative? It is, I think that, no, it's just 24.83% of our data. And then at 6.8, so I'm done with that. I'm just like clicking on too many tabs. At 0.68 here, we have 0.7517. So we have 0.7517. Is that what I said? 0.7517. 0.7517 at 0.68. 0.7517. That's correct. And then over here at 1.25, we'll do 1.25. We have 1.25 is 8944. 0.8944, and at negative 1.25, at negative 1.25, right here we have 1.25, 1056, right, 0.1056. And so if we find the difference between those two, for the middle we have 0.8944, the largest amount of the data, minus the 0.1056, and the difference over here will be 0.7517 minus 0.2483, and we'll bold these, I guess. Boom. I kind of like that. And bold this. Boom. And boom. And then we will calculate these, and we'll come over here and put that in, and we get this, and that's what we had before. I guess that's fine, 0.05, and we'll do this one, and we have this, right? Ah, that makes sense. I just had a little bit of a, oh yeah, that's right. And so here, right, 78.888% of our data is within, right, when we have more samples, we're describing more data within the $500 range. There's a higher probability that the population parameter, the population mean, is going to be within $500 of our sample mean. And here, there's a 50.34% probability And so how do we go from that to getting this curve here where it's tighter? That's the maybe probability density function. And what we're calculating here is just the probability. I'm just trying to picture that. That's what I was trying to picture, is how did this get tighter, right? Like our standard deviations are capturing more data within $500, so that has to make it tighter, right? So between 71,300 and 72,300, more of the data is being captured. 78% of the data is being captured, so that we have to have more within that range, versus here, less of the data is being captured, so more of the data is stretched out to the left and the right. Just thinking it through. So that's how those calculations go, and I think that's pretty good to walk through that. And that's the relationship between the sample size and the sampling distribution. And we'll just see if there's anything else here to say. Oh, there's actually 2 more slides. Recall that when we showed n equals 30, now 788, we just did that, 788. And because of the sampling distribution with n has a smaller standard error, the values of the sample mean have less variability, so that's the standard error. So here's less variability, here's more variability, and here's less variability, this tight one, and then the wide one is more variability. So I like that description. Less variability, and tend to be closer to the population mean than the values of the sample mean with n equals 30. And then here is the relationship, the same title, but this is 78.88% of our data is in that range, and that's what I was trying to describe there. That was kind of fun. I like trying to figure things out and talk them out and make sense of them. I hope that was helpful to you. In the next video, we'll learn some more stuff.